Okay, the 9.2 quick check is a little bit on the subtle side here. So we're starting off with the Lewis structure of carbon dioxide, and we want to use a more sophisticated model. We want to use our hybrid orbitals to talk about what kind of bonding goes on in CO2. So we start off with the Lewis dot structure. So carbon, we know, has a carbon in the middle, and if it's with an oxygen, each has 6 valence electrons. Carbon has 4 valence electrons, and so we get a picture like this where we have 2 double bonds on that carbon. So we say, well, how many sigma and pi bonds? Well, that part's actually kind of easy. So if we have a double bond, we know a double bond is a sigma and a pi. So I have a sigma here and a pi for that double bond. I've got a sigma and a pi for this double bond. So I'm going to have 2 sigmas and 2 pi bonds in a CO2. And remember that those lone pairs do not count as bonds, so don't count them at all. So indicate the hybridization used by each atom. Okay, well, if we look at this, we can see that that carbon has a steric number of 2 bonded atoms, no lone pairs. So that's going to be an sp hybridization. And each of the oxygens has 1 bonded atom, oxygen bonds to the carbon, and 2 lone pairs. So they're going to be steric number of 3, so they're sp2s. Okay, and what that reminds us then is if we have sp2, that means there are 3 sp2 orbitals, okay, because it used to be an s and a p and a p, and then there's also a p left over. So the sp2, 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 and a p, and that sp2, those are going to be in a trigonal planar arrangement with the p coming out the middle. Okay, describe and draw the molecular orbital, that balloon diagram. So here we go. So we have sort of carbon dioxide. I'm going to color code a little bit, and I'm going to say that one of these pair of electrons is going to be in a sigma bond on each side, and one of those pairs of electrons is going to be in a pi bond. Okay. In fact, what I'm going to do is I'm going to make one pi bond one direction, one color, and pi bond in the other direction, another color. So let's try that. So I'm going to start off with my carbon. My carbon atom, I know, has sp hybridization, steric number of 2. So it has an sp orbital this way, and it has an sp orbital like this. Okay, now those are going to bond onto the oxygens. We'll do that in a minute. Okay, but this carbon also has a p orbital that's going to go up and down, and it's got another p orbital at right angles. I'm going to do it at 45 degrees. So those are my sp, those are the 2 blue 2 sp orbitals, and then a green p orbital and a red p orbital. Okay, on the oxygen on the right, okay, I'm going to put that in as a sp2 hybrid, steric number 3, sp2 at 120 degrees, and I want that to match up with my green, so I'm going to draw my sp2 this way. I'm going to draw my sp2 down a little bit, and one that's behind it. So these are perpendicular to the board, and that means I have room for a p orbital straight up and down. So sp2, 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 and I have a p orbital. And that means my green here is going to be able to blend together to make a pi bond above and below the plane of the molecule. And so I'm going to color this all in. So all of this green area counts as one big pi bond. And the same thing up here. One big pi bond. So far what I have is I have a sigma right here. These are lone pairs. And this is a pi. So a sigma and a pi, just like we said right here, that's a sigma and a pi between the carbon and the oxygen. Now in the other way over here on the left, then I'm going to put an oxygen. Okay, and this time I'm going to use the red p orbital. So for this oxygen, I'm going to do 120 degrees, but I'm going to do it in the plane of the board. And that means I have room for my pi bond, my p orbital to go like this. So in my lone pair, I'm going to put my lone pairs into those orbitals there. This is a sigma bond. And then the pi bond is going to be these p orbitals blending together in front of the molecule. And also back here behind the molecule, So in front and the back of the molecule, it's going to look something like that. Okay, so hopefully you get the sense that the pi bonds here, the red pi bond, the red pi bond and the green pi bond are 90 degrees from each other. So here's my carbon, here's an oxygen, okay, and two pairs of electrons, one shared in the sigma, okay, sigma bond right here. I'll blue it in, okay, and then I have another sigma bond here where my orbitals are overlapping. I'm going to draw that in and go back and relabel sigma and sigma. Okay, and then there's a pi and a pi, and the pi's are at right angles to each other, and that's CO2. Okay, for acetic acid, here is one where we wanted to kind of go back and learn something, and that is, that we saw a long time ago that the COOH, carboxylic acid grouping there, and that an acid is something that releases H plus ions, and this H there is the one that takes off as an H plus. So we wanted to learn why, and the short answer is, when that leaves and you have the acetate ion, it does resonance, so the electrons get to spend their time on both of those atoms, all three of those atoms, and that stabilizes it a little bit. So let's go back and look. It says fill in the lone pairs on these structures. Okay, so I'm going to redraw my structure. Okay, so I have C double bond O, H, and something that we always leave off when we do structural formulas is we leave off those lone pairs on the oxygens and also on hydrogens. Now we say what happens then is that this hydrogen is the one that leaves. The other hydrogens don't do that, but this one leaves about 1 to 2 to 3%. That's why it's a weak acid. Well, when that happens, okay, what are we supposed to say? Fill in the lone pairs, indicate the hybridization, and draw the balloon diagram of the acetate ion. Well, we can see right here what happens is that this guy is sp3, steric number 4, sp3, and this one here is sp2, and this one is sp2, and this one looks like it's sp3, okay? But when that hydrogen takes off, this changes a little bit. So over here, okay, we have our acetate ions. Now this is shortcut, okay, very shortcut. And what happens here is, we just end of the line, and that means that that's a carbon, and if there's a carbon, there's 3 hydrogens on it. So, we really are putting a shortcut. So I'm going to redraw this so we can see it a little bit better. And what we're going to have is we have a carbon, okay, double bonded to an oxygen, single bonded to an oxygen, okay, and then this hooks to another carbon. This is our acetate ion with a negative charge. And we're going to put our lone pairs in. This has 2 lone pairs, this has 3 lone pairs. And this would have a resonance structure. And the resonance structure will look very much the same. So carbon, C, but here I can put a single bond this way and a double bond down. Okay, that's where my resonance idea is. Put my hydrogens back in. And so now I would draw this with 3 lone pairs and with this 2 lone pairs, and give it a brackets and a charge. So these atoms here are involved in resonance, and we want to try to show, well, what's going on. So we know in resonance everybody is really sp2. Even, so if I said, well, what's sp2? This guy looks like sp2, and this looks like sp2, but this one looks like sp3, but it's not. It's really sp2. So again, these two look like sp2, that's fine, but this is also really sp2. So they're all trigonal planar. So we're going to try to draw that. So I can say, here's my carbon, and if I'm doing trigonal planar, I'm going to put one orbital out this way, one coming down, and one going behind it. Okay, and that's they're 120 degrees, and then they have a p orbital left over, up and down. So sp2, 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 and a p orbital. Okay, another oxygen over down here. This is this one over here. Okay, then it's going to do sp2, sp2, and the sp2 out this way. So these are going to blend together and make a pi bond. And it has a p orbital up and down that we're going to use. Okay, I think I said that wrong. These are blending together to make a sigma bond right between the two. Okay, so this is going to be a lone pair out here, it's going to be a lone pair out here, and this is a sigma bond here in between. Now I have my other oxygen. Okay, I'll put it back here, and I'm going to make it gray. And so it has sp2, sp2, and sp2, okay, at 120 degrees, and it also has a p orbital up and down. So coloring these in, okay, I get a sigma bond right here. And I'll label that. And there's a lone pair here and a lone pair there. Okay, I'm going to go back and clean up that lone pair. Okay, so now my p orbitals here can blend together. Okay, but not only blend that way, they also blend over this way. So I get this big V-shaped p orbital pi bond that is above these atoms. So right above the C and the O and the O, then there is a orbital floating above that. That's kind of a big V-shaped, or however you want to talk about it. Okay, and the same thing is happening down here below. Now it's kind of hard for it to see where it goes, but it's coming back over here on the other side. So it's the same shape as the one above, it's just down there below these atoms. And remember, every time we do this resonance and we blend p orbitals, then we also get, two of these pi bonds, because there's always one above and one below the molecule. So that whole big thing is one big pi bond. So I have a sigma, sigma, and a pi. Okay, but finishing things up, I have another carbon over here, and it's doing sp3. It's steric number 4, sp3. So I'm going to draw those and then put one more in, like here. So I have 4 things. And there are hydrogens sharing their 1s orbitals over here. Okay, so these are all sigma bonds. I got a sigma bond here, I have a sigma bond here, I have a sigma bond here. And this is a sigma bond here. So there's my sigma, there's a sigma, there's a sigma, there's a sigma. And I'm going to try to clarify these a little bit. Okay, so here's hydrogen, 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 carbon, carbon, oxygen, and oxygen. Okay, and because the electron gets to spin in this kind of red area, electrons get to spread out over all 3 atoms. That stabilizes this guy a little bit, okay, and makes it stable enough so that a hydrogen ion can take off by itself, okay, which is just a proton. And that is the bonding that we want to show for the acetate ion. So when we do way back here for this kind of a picture, just a little double arrow, it really implies all of this in our bonding diagram. And that's what's going on with the acetate. Okay, the last part of this is molecular spectroscopy. And the idea here, I'd like to make one change. Here on C, I said one of the options was bond rotations, and bonds don't rotate. A molecule could rotate. So if I had a molecule that looked like this, okay, then this guy could go this way, this guy could go this way, and the whole molecule could rotate. But, a bond doesn't rotate. A bond vibrates, and we've seen that where we have an atom and an atom, and we saw on the movie like a little spring, and so it could, vibrate back and forth, but that's different than rotating. So what do we know? UV visible light, that causes valence electrons to get excited. That's answer D. Microwaves causes the rotations. X-rays, that's PES. And that's where we're exciting the core electrons right out of the atom. So it just totally ejects those. And infrared is causing bond vibrations. Okay, and that's important stuff. On the AP curriculum, we are required to teach about this one, and this one. You're supposed to know that. So UV vis, we do that all the time with colorimetry, when we were trying to figure out what is the concentration of a colored ion or something. Okay, PES, that's what we're doing. We were doing like 1s2, 2s2, 2p6, 3s2. We're doing those little PES spectra. And infrared is just the idea that you can make different bonds vibrate. So like a triple bond would vibrate at one frequency, and a double bond would vibrate at a different frequency. And a triple bond is much stronger, so it's going to have a higher frequency than a double bond, stronger than a single bond, things like that. Okay, so a researcher wants to use spectroscopy to differentiate between ethane, that's a single bond, and ethene. Which type of electromagnetic radiation would be the best choice? Okay, the best choice, infrared, because that's going to cause the bonds to vibrate. And if we were looking at a spectrum, okay, that as we go through different frequencies, okay, then maybe a low frequency would cause the double bond to vibrate. Okay, a higher frequency would cause a triple bond to vibrate. So where it absorbs energy to cause these guys to vibrate is what we can tell from an infrared spectrum. And that's the whole quick check.